Section 1 Introduction. Our topic for discussion revolves around the enhancement of large language models, LLMs, such as ChatGPT, which are being developed to function as AI assistants. These models have made significant strides in recent times. However, they are not without limitations. For instance, they struggle with understanding visual environments and comprehending complex tasks, both of which limit their usefulness in real-world applications. We've been looking at ways to overcome these limitations. One potential solution that shows promise involves combining the efforts of multiple domain experts, like pre-trained models or APIs, to manage more complex tasks. Several attempts have already been made in this area. Some researchers are using language to bridge the gap, converting visual input into text with basic visual models like object detectors, OCR models, and captioners. These transformed texts are then processed by LLMs to solve reasoning tasks such as question answering. However, when dealing with more complex visual situations, such as lengthy videos with intricate scene changes, the resulting texts often include excessive, unnecessary information, while neglecting crucial details that directly answer the query. An alternative approach involves breaking down user queries into smaller tasks and sequentially calling upon external models or APIs to address them. Current methods can be divided into two main categories: language-based planning and code-based planning. The former involves using an LLM to manage the cooperation of expert models, while the latter leverages codecs to write Python code, which in turn calls upon visual-related APIs for handling multimodal tasks. These methods optimize computational resources by ensuring that models are only invoked when needed. However, even with these advancements, addressing high-level queries remains a challenging task. Existing benchmarks typically offer hints on planning the reasoning process. For instance, if asked, "What is the red object used for?" the reasoning steps are usually fixed, regardless of the image. Identify the red object, then deduce its function. However, complex questions may require diverse reasoning paths, depending on how the information is presented. This is why we are proposing a multimodal AI assistant system called AssistGPT. Our system combines the benefits of flexible reasoning found in React and robust tool invocation in program-based planning. It consists of four components: the planner, the executor, the inspector, and the learner. Our planner works much like the one in React, considering what needs to be done next based on the current reasoning progress and invoking external models. However, our planner differs in that it uses formatted code to invoke these models. The executor ensures a uniform input and output format across all external tools, allowing the tools to be invoked with structural commands. To manage visual inputs and intermediate results during the reasoning process, we have an inspector that provides summaries and metadata of all currently available visual materials. Given the complexity of ensuring correct reasoning in a zero-shot scenario, we introduced the learner. This component checks the reasonableness of the prediction process and the correctness of predicted results, enabling continuous improvement of the system. The current version of AssistGPT integrates over 10 different tools, including image detection, captioning, region grounding, temporal grounding, OCR module, object enumeration, speech-to-text, and more. When these functionalities are combined, AssistGPT can handle a wide variety of multimodal tasks that remain challenging for existing systems. In conclusion, we have developed a versatile multimodal AI assistant capable of completing a wide variety of visual-related tasks with the help of multiple models. This system incorporates a unique method of reasoning that alternates between language and code. Furthermore, we've introduced a simple learning mechanism to improve AssistGPT's planning abilities. We demonstrate AssistGPT's capabilities not only in benchmark results but also in realistic applications for processing complex images and long-form videos, understanding high-level queries, and handling flexible inputs. Section Summary. The paper discusses the limitations of single large language models, LLMs, in AI assistants and proposes a solution of integrating multiple domain experts to tackle complex tasks. The proposed multimodal AI assistant system, named AssistGPT, uses interleaved language and code reasoning method and consists of four parts: planner, executor, inspector, and learner. The system integrates 10+ tools for different functions and can accomplish a wide range of multimodal tasks, including processing complex images and long-form videos, understanding high-level queries, and handling flexible inputs. Section 2 Related work. Before large language models, LLMs, came onto the scene, a lot of work was done to create models that could handle multiple types of inputs, including those relating to visual elements, actions, text, and more. While these models achieved notable success in their specific tasks, they weren't as effective when it came to handling a wide variety of real-world scenarios. With recent advancements, two strategies have been proposed for creating more general multimodal systems. The first strategy involves pre-training LLMs to use visual elements as conditional inputs. Notable models using this approach include GPT-4, PaLM-E, BLIP-2, and Mini-GPT-4. While these models can handle multimodal inputs, they still face limitations when it comes to understanding more advanced tasks, like interpreting spatial relationships in images or comprehending audio. Also, these models can be computationally expensive to scale up. The second strategy involves combining multiple models or tools to carry out complex multimodal reasoning. For example, the Socratic model and Visual Chat GPT use this approach by connecting the text-based Chat GPT with image-generating models. Hugging GPT merges various Hugging Face models with LLMs, while Viper GPT utilizes codecs to access visual APIs through Python programming. Our model, AssistGPT, falls into this category as it combines different modules for multimodal reasoning. However, we're introducing a new framework called PEIL, which allows for the integration of external tools and models. Turning to compositional reasoning, this approach breaks down questions into smaller tasks, each handled by a specific module. It's a popular method in visual question answering because it provides clarity about what each component of the system is doing. Traditional compositional reasoning methods have been limited by the language parsing capabilities of models and often require explicit question decomposition or reinforcement learning. However, LLMs have now made it possible to break down questions effectively without any prior instruction. Examples include models like Chain of Thought Prompts, Toolformer, and React, which help models plan their problem-solving approach. Models like Hugging GPT and Viper GPT use LLMs to divide a question into a series of reasoning steps. But, for complex queries, these models need to factor in visual inputs or feedback from previously run modules, which adds another layer of complexity. The React model attempts to address this challenge by introducing the idea of React into a multimodal system, but it's still being developed and hasn't been validated on benchmark tests. Our work is novel because it introduces an approach that intertwines language and code reasoning, addressing some of the limitations of earlier methods. This can better handle general queries and complex visual inputs. In terms of training schemes for modular systems, early models typically used end-to-end reinforcement learning to train each module from scratch. While this method works for smaller models, it can be burdensome for larger systems where each module is an LLM. Toolformer offers a self-supervised approach that optimizes planning with just a few examples for each API. It tests different APIs to find successful approaches and then fine-tunes the model based on those results. We propose a simpler mechanism for multimodal fields, guiding the system to retry tasks and preserve successful attempts as in-context examples. Section summary. Prior to LLM, multimodal models were designed for specific tasks, but their generalizability was limited. Two strategies have been proposed for developing a general multimodal system: pre-training LLM and combining multiple models or APIs. Compositional reasoning methods decompose questions into subtasks, but LLMs can accomplish question decomposition in a zero-shot manner. Early modular models employed end-to-end RL, but our work proposes a straightforward mechanism to guide the system to retry and preserve successful explorations as in-context examples. Section 3: AssistGPT. We're going to explain AssistGPT, a dynamic AI system that interfaces with various tools in a conversational manner. By taking both text and reference images or videos as inputs, AssistGPT works to generate the required responses. The functioning of this system is driven by four central modules: Planner, Executor, Inspector, and Learner. The planner, like the director of an orchestra, controls the entire problem-solving process. The executor collaborates with the planner by utilizing external tools and providing essential feedback. The inspector manages the initial inputs as well as any intermediary results, helping the planner feed appropriate content to the executor. The learner, like a tutor, evaluates the system's performance and records successful explorations as in-context examples. Our journey begins with the planner, which uses the state-of-the-art language learning model GPT-4 as its guiding intelligence to direct global reasoning and planning. The planner takes in three types of inputs: the instruction prompt, which consists of the toolset and in-context examples, the input query, and the summary of visual inputs created by the inspector. The planner then generates an output that is composed of a thought and an action. The thought is a language phrase indicating the next step in the process. It doesn't directly influence the module or the API call but guides the learning model in planning the next move. The action, on the other hand, is a structured string conforming to a predefined template. It clearly dictates which external tool to use and what arguments to input. For instance, asking a question about an image like, "What color is the car?" to the caption tool. Once the executor makes a call to an external tool, it receives outputs in natural language called observations. If the tool produces an intermediate result, for example, a segmented video, the inspector saves it and creates a summary. The planner then uses both the observation and summary to guide the planning of the next step. In our AssistGPT system, we currently have 13 functional tools that empower multimodal assistance. These tools fall into three main categories: descriptors, locators, and reasoners. Descriptors, like our sensory organs, help understand and utilize data derived from complex multimodal environments, such as images, videos, audio, and text. We use several fundamental models as descriptors to interpret these sources, including image caption, video narration, object detection, text detection, and author translation. Locators, like a treasure map, help pinpoint the most critical information from the wealth of visual, textual, and audio data. These modules, including region ground, narration ground, text ground, and subtitle ground, help extract the most useful information. Reasoners, as their name suggests, deal with reasoning and problem solving. They use the extracted information and external knowledge to solve problems or answer questions. This category includes the knowledge reason, narration reason, subtitle reason, and temporal reason modules. These tools utilize language learning models at their core and take different types of information and prompts as inputs. Section summary. AssistGPT is a multimodal AI assistant system that generates answers to general language queries using reference images or videos as inputs. It consists of 4 core modules: planner, executor, inspector, and learner, which work together to control the reasoning process, execute external tools, manage input and intermediate results, and assess system performance. The system integrates 13 functional tools, including fundamental models for perception, modules for pinpointing crucial information, and modules for reasoning using extracted information and external knowledge. Section 3.2 Executor. The 3.2 section talks about the executor's role, which is a crucial part of the system. It primarily takes the generated code from the planner as an input, then uses it to produce the final output. This involves 3 key steps, which are the validation check, the module execution, and the post-processing. Validation check. The executor initiates the process with a validation check. Despite the advanced capabilities of large language models like GPT-4, there's always a chance that they might generate erroneous or incompatible code. An instance would be when an image captioning module tries to process a lengthy video. To counteract such issues, we've implemented a legality check for each module. This way, we can determine whether the code can be executed without causing any errors. If the code does contain errors, we don't completely halt the reasoning process. Instead, we send back an error message as an output code to the planner, which then helps in optimizing the planning process in real time. Module execution. Next, we execute the validated code. To facilitate this, we have standardized various modules or APIs into a unified interface, which is structured as module_name, less than text_query greater than, less than visual_index greater than. Every module in this structure is designed to handle multiple text queries and visual data inputs, which could be either images or videos. Moreover, to make the planning process more straightforward and accurate, the generated code is simplified. A simple rule-based function is used to translate this simplified code into executable codes, which are then run to get the final result. Post-processing. The last step is post-processing. The results generated from all modules are converted into a language format that can communicate the outcome to the planner, just like the observation part mentioned earlier. For example, the narration ground module would return whether it has located the relevant segment. If it has, it would output the start and end times of this segment. Many ground-related modules also send their processed video segment or cropped image region to the subsequent visual outcome manager, known as the inspector. Section summary. The executor takes the code generated by the planner and carries out 3 steps to obtain the final result: validation check, module execution, and post-processing. The validation check ensures that the code is executable and returns an error message to the planner if there are errors. The module execution standardizes various modules or APIs into a unified interface and simplifies the generated code, which is later mapped to executable code. Finally, the post-processing translates the generated results into a language format to inform the planner about the outcome. Section 3.3 Inspector. Our Inspector feature aims to manage the visual inputs offered by the user, as well as the intermediary results our system produces. This assists our planner in making decisions about which source should be directed to which module. Specifically, the inspector keeps track of the metadata of each visual element. This metadata includes the type of the visual element, whether it's an image or video, its source, i.e., whether it was supplied by the user or generated by our system, and a concise description of its content. This description can be acquired from the caption model or, in the case of online videos, the video's title. For videos, the inspector collects additional metadata like the duration of the video and whether it has audio and subtitles. The inspector keeps an eye on both the inputs from the user and the outputs from the executor. Whenever a new visual element is received, it attaches the corresponding metadata, referred to as summary, above, to the planner's reasoning history. With the collaboration of the planner, executor, and inspector, our system is capable of generating answers to complex queries with complex visual inputs. Section Summary. The inspector manages visual inputs from the user and the system to assist the planner in deciding which source should be directed to which module. It records metadata of each visual element, including type, source, and content description, and monitors inputs and outputs to append metadata to the reasoning history of the planner. With the cooperation of the planner, executor, and inspector, the system can generate answers to difficult queries with complex visual inputs. Section 3.4 Learner. We're implementing a feature we call the Learner to address potential issues our AI, AssistGPT, may face when handling multimodal queries. The learner function helps the AI to self-assess and verify its own output's reasonableness, crucial for avoiding errors. Moreover, if a correct answer is provided, what we term as ground truth, our system attempts to gather these successful predictions for use as in-context examples in the future. Essentially, AssistGPT will keep trying to generate satisfactory responses. It will continue to do so until it either self-validates the output, provides the correct answer, if a ground truth is available, or reaches a predefined limit on the number of attempts. The learner has an evaluator, created by the language learning model, LLM, that functions in two ways, self-assessment and ground truth comparison. Which mode is used depends on whether or not ground truth is available. In self-assessment mode, where there's no user feedback or ground truth, the AI reviews the logic and results of each step to ensure it's complete, consistent, and formatted correctly. When a ground truth is provided, the AI activates the ground truth comparison mode, comparing its prediction with the ground truth to verify if they're semantically consistent. The learner is designed to keep trying until it gets positive feedback or reaches its attempt limit. Following a number of attempts, let's call it n, several situations can occur. 1. No adjustments required. If the AI provides the correct answer on the first try, this indicates that AssistGPT is successfully handling the current question, and no further improvement is necessary. 2. Plan revision. If the AI produces the correct answer after n attempts, where n is more than 1 but less than or equal to n, it implies that the model's planning could be improved. In such cases, we store the successful logic chain in what we call the in-context memory bank. Then, if a similar query appears in the future, the model can refer to this as an example. 3. Function updates. If after n attempts, the model is still unsuccessful, it's likely that the issue is within a particular module or API, not the planning process. These modules may need incremental updates, something we will consider for future iterations of the model. Section Summary. AssistGPT has a self-evaluation mechanism that allows it to check the reasonableness of its output. It operates in two modes, self-assessment and ground truth comparison. The model encourages repeated attempts until it receives positive feedback or reaches the maximum number of attempts. If the model delivers the correct answer on its initial attempt, no improvement is required. If it produces the correct answer after making n attempts, where 1 less than n is less than or equal to n, this implies that there is room for improving the model's planning capabilities. Section 4 Experiments. We conducted some experiments to test the capabilities of our system. Section 4.1 describes the experimental setup. We tested our system using two distinct benchmarks, known as A-OKVQA and NExT-QA. These are specifically designed to test a system's ability to handle a variety of multimodal tasks, such as understanding visual elements, applying common sense, interpreting sequences over time, and deducing causal relationships. The A-OKVQA benchmark is a novel tool for testing how well a system can answer questions about visual data using its understanding of common sense and general knowledge. It includes a substantial 25,000 questions, each requiring a deep comprehension of the world. These questions go beyond the contents of a given image, so they can't be answered by merely accessing a database of facts. Instead, they cover a broad range of domains, from common sense reasoning to knowledge-based understanding, from visually grounded interpretation to physical understanding. To evaluate our model, we tested it under what we call the in-context learning setting, using a validation set of 1,145 questions from this benchmark. On the other hand, the NExT-QA benchmark is designed to assess an AI system's ability to reason about causality, temporal action, and object interactions in the context of video question answering. It includes a total of 5,440 videos, each averaging about 44 seconds in length, along with approximately 52,000 pairs of manually annotated questions and answers. Again, we evaluated our model's performance using the in-context learning setting, this time on a validation set of 4,996 questions from this benchmark. As for the technical details of our experiments, we use the GPT-4 API provided by OpenAI as our planning tool. For the A-OKVQA trials, we configured our caption module as either blip2 or instruct blip. We abbreviate this as INS. Blip. We also used the grounding Dino model for object detection and the Google OCR tool for text detection. For the NExT-QA trials, we based our video narration module on the instruct blip Vicuña 7B model. We conducted all of our experiments using 4 A5000 graphics processing units, GPUs. Section summary. The system is evaluated on two benchmarks, A-OKVQA and NExT-QA, which test multimodal capabilities including visual facts, common sense, temporal sequences, and causality. A-OKVQA has 25K questions that require high-level comprehension of common sense and world knowledge, while NExT-QA has 5,440 videos with approximately 52K manually annotated question-answer pairs. The experiments were performed using GPT-4 API provided by OpenAI as planner and implemented on 4 A5000 GPUs. Section 4.2 Quantitative Results. Section 4.2 Quantitative Results. Comparing with top-tier methods when analyzing the data presented in our table, it's apparent that our two iterations of AssistGPT, namely, the less intensive blip2 flant5_XL, and the more robust INS blip Vicuña 7B, outperformed all other existing techniques in the context-based learning setting, specifically within the multiple-choice segment. Notably, we utilized a pre-trained version of instruct blip, achieving a performance score of 53.3%. However, when integrated into our system, its performance was elevated to the standard of a fine-tuned model. For questions requiring a direct response, we admit our model did not surpass the performance of some newly proposed models. Nevertheless, it is on par with earlier top-performing models, such as GPT-2. The primary cause for this is that models based on language model, LLM, for open-ended queries tend to generate comprehensive phrases instead of single-word answers, regardless of how much we prompt for brevity. For instance, if asked, "What flag is represented on the wall?" our AssistGPT might respond with, "United States flag." Unfortunately, if the desired answer doesn't include the word flag, it's marked incorrect. This type of error is quite common with AssistGPT, and more examples are available in the appendix. Compared to the state-of-the-art method, PromptCap, which is specifically trained to create captions for A-OKVQA, our model showed higher versatility. As for why AssistGPT performance excels in addressing causal and descriptive questions, it's largely because our model consistently fetches detailed, question-related information from videos. However, our model did not perform well on temporal questions. The lack of open-world temporal grounding models is a key factor here. Currently, the norm is to fine-tune models on closed-world datasets. Thus, we had to combine the image captioner instruct blip with GPT-4 to achieve temporal grounding, and although this didn't achieve the same results as the fine-tuned models, it offered greater generalization capabilities. Our model's performance is also very close to a recent similar work, Viper GPT, which slightly outperforms ours, possibly due to its sophisticated rule-based approach, iteratively checking whether objects appear in the frame to perform temporal grounding. We developed various AssistGPT iterations to evaluate the effectiveness of our methodology. Our most fundamental baseline is instruct blip, which serves as the primary source of visual information in AssistGPT. To address the issue of instruct blip not necessarily producing the desired answer format, we designed a variant named instruct blip plus GPT-4, which allows GPT-4 to refine instruct blip's output further. We also created a reason-only model that lays out all the required execution steps for the models, akin to previous works. Moreover, we introduced the React model, capable of executing language-based reactions, but lacking inspector and code-like invocation capabilities. We also introduced a variation, the learner, in 3 iterations, PEIL with self-check, and PEIL with GT-check. The reason-only model, which plans all necessary steps for the models to execute, showed significant improvement in direct answer, DA, and multiple choice, MC, indicating that integrating multiple models can enhance performance. The React model, even without inspector and code-like invocation capabilities, showed further improvement in both metrics, surpassing the reason-only model. Including our interleaved language and code, PEIL, led to an even more substantial improvement on MC. The two PEIL variants with partial ablations, PEIL with self-check, and PEIL with GT-check, scored the highest on both tracks, illustrating the effectiveness of the learner. The learner showed a more significant improvement on DA tracks as models often fail to provide extremely short answers required by A-OKVQA, an issue the learner mitigates by collecting in-context examples. Section summary. The two versions of AssistGPT achieve the best performance among all current methods on in-context learning setting for multi-choice questions. While our performance on direct answer questions is comparable to previous supervised SOTA, we tend to output complete phrases rather than a single word as the final answer, resulting in errors. The reason-only model showed a notable improvement in DA and MC, but the two variants of PEIL with partial ablation scored the highest on both tracks, showing the effectiveness of the learner. Section 4.3 Qualitative Results. In Section 4.3, we've presented some visual examples of predictions made by our model, AssistGPT, for two different questions from the A-OKVQA and NExT-QA databases. The model's workings are demonstrated, as it breaks down the questions into manageable subtasks and tackles them one at a time until the final answer is reached. An important aspect of our model is the way it interweaves code and language reasoning methods. This allows AssistGPT to effectively use the necessary content as an input. A clear instance of this can be seen in how it handled question 1. AssistGPT also has a self-correcting ability. For example, if the visual model produces less than satisfactory results, AssistGPT can switch to using other modules, like the ground module, to reason along a different path. In the case of question 1, the model's initial approach didn't yield effective results. But AssistGPT doesn't stop there. It independently fine-tunes the plan when it doesn't pass its own self-check. We also compared AssistGPT with a reason-only baseline model. This other model first uses instruct-blip to generate a caption and then uses GPT-4 for inference. However, if the caption's information doesn't meet the requirements, it can lead to incorrect results. And unlike AssistGPT, once this model makes an unsuccessful prediction, it doesn't have a mechanism to self-optimize. We would like to highlight that one of the greatest strengths of AssistGPT is its ability to tackle more complex problems than those typically found in benchmark tests, as demonstrated by the example shown in figure. We've provided further examples of how our model performs with real-world scenarios in the appendix. Section summary. The AssistGPT model can effectively decompose complex questions into subtasks and complete them step by step, with the ability to self-correct and optimize its plan. In comparison, the reason-only baseline model fails to meet requirements and lacks the ability to self-optimize. The AssistGPT model can solve more complex problems than those in the benchmark, as demonstrated in the presented examples.